Hello students and welcome to the lecture. So students, as you can see here that basically in this lecture we are going to start the discussion over the viscosity. Okay, and this is going to be our part 1. In this lecture basically we will talk about the introduction, distinction between viscosity and solid friction, Poiseiulle formula, Stoke's law, terminal velocity. So these are going to be our content for discussion, like starting with the introduction, then the distinction or difference between the viscosity and solid friction, Poiseuille's formula, Stoke's law, and terminal velocity. But before starting the lecture, as usual, we have our small disclaimer over here that we are required to understand before we proceed further. The disclaimer is like the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this tag and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Now, let's begin with the introduction of the viscosity. So, what do we actually understand by the viscosity? What is the meaning of this? So, we could say the viscosity is actually the property of the fluid, liquid and gas. Okay, there is a always misconception amongst the students, like whenever they see the fluid, they only considered it as liquid. Okay, this is the highest misconception you can say which I have seen in the students. Like whenever they are seeing fluid, they always considered liquid only, and when we go by the physics, so in physics we consider the liquid and gas both. Okay, so remember, because right now we are covering the physics, so whenever we talk about fluid, we are not only talking about the liquid as we take it in the layman terms or common language. In physics we talk about fluid considering the liquid and gas both, so both will be considered. Okay, so viscosity is actually the property of the liquid and gas by virtue of which an internal resistance of friction comes into play when a liquid is in motion is called viscosity. So we could say in the layman terms, like whenever we having a liquid or gas, whenever liquid or gas in the motion, okay, so they having a different layers. Okay, so their different layers possess the internal resistance of friction while playing into motion, and this property of a liquid or gas known as the viscosity. So technically viscosity is actually the property of liquid and gas, or simply we could call it as a fluid. Viscosity is actually the property of fluid by virtue of it having a capacity of providing the internal resistance of friction while in a motion. Okay, it opposes the relative motion of different layers. Like as I have told you, fluid, mainly the liquid and gas, they having a different layers. Okay, and whenever they are in the motion, their different layers are in a motion. Okay, so these different layers facing a relative motion, and that relative motion is actually being resisted by the internal resistance or the friction that we call as the viscosity. Okay, in viscosity, a backward dragging force acts tangentially on the layers of the fluid in motion and it tries to stop the motion. Okay, now what is the coefficient of viscosity? Technically, so far we have talked about the viscosity. Like we know viscosity is the property of internal resistance of friction in fluid. It actually opposes the relative motion in the different layers of fluid, and it is a backward dragging force that acts tangentially on the layers of the fluid in motion and tries to stop it. Now let's have a talk about the coefficient of viscosity. Like what is the coefficient of viscosity? So experimentally, it is found that in a flowing liquid, the stress is proportional to the rate of change of strain or strain rate. Okay, it is different from solid where stress is directly proportional to strain. Okay, Like in the viscosity, stress is proportional to the rate of change of strain, like not to the strain or strain rate, but basically on the rate of change of strain. Like at rate which the strain is getting changed, the stress will be proportional to it. While in solid, the stress is directly proportional to strain, not to the rate of change in strain. Got it? Now, for the flowing liquid, the rate of change of strain rate is actually presented by change in shear strain by time interval. Okay, like delta x by L by delta t equals to V by L. Shearing stress equals to F by A. The coefficient of viscosity eta for a fluid is defined as the ratio of shearing stress to the strain rate. Remember this, this is important. In the coefficient of viscosity, which is presented by eta, for a fluid, the ratio of shearing strain to the strain rate is actually the coefficient of viscosity. Therefore, eta equals to shearing strain by strain rate equals to F by A by V by L equals to F into L by V into A. Got it? This is the coefficient of viscosity. If dV is the difference in velocity of two layers of moving liquid, like we know in fluid or mainly in the liquid or gas, there are the different layers. Okay, maybe the layer 1 upper layer, then layer 2 down layer, layer 3 mid layer, layer 4, okay, lower mid, or you can say layer 5. This is the lowest layer. So now you can say, by taking this example, we could say that they are the different layers. Okay, so whenever the fluid or liquid is in a motion, automatically these two layers are in a motion. Okay, and if we talk about the difference in velocity of these two layers of moving liquid, so we could say distance dx apart then v by l equals to dv by dl, velocity gradient between two layers of liquid. Now eta equals to f by a into v by l equals to f by a into dv dx. If a equals to 1, then dv by dx equals to 1, then eta equals to f by 1 into 1 minus f. Okay, thus the coefficient of viscosity of liquid is equal to the tangential force required to maintain a unit velocity gradient between two parallel layers to liquid each of area unity. Dimensional formula of eta is bracket ml's power minus 1 into t's power minus 1. The SI units of coefficient of viscosity is Poiseiulle, PL, or Pascal's powers minus 8, or Newton meters power minus 2 seconds, or you can say kgm's power minus 1 into seconds power minus 5. Now, after taking the introduction to the viscosity, after understanding this, now let's have a talk over the distinction between the viscosity and solid friction. What is the difference between the viscosity and solid friction? That is we required to understand. Like we know, fluid also having the internal resistance, okay, or the internal friction, that we call as a viscosity, and we know solid also having this kind of thing. So now what is the difference between the viscosity, that is the internal resistance of fluid, with the solid friction? So viscosity is similar to the solid friction in the respect that both come into play whenever there is a relative motion. Like we know, in solid, whenever the solid is in the motion, automatically the solid friction will come into play. And we know whenever the fluid is in a motion, automatically the viscosity comes into the play. So whenever the layers are in the relative motion, solid friction and the viscosity both will come into the play. So they are similar in that respect. Both oppose the relative motion. We know that this is the internal resistance. Okay, that's why they are basically opposing the relative motion. Both are due to the molecular forces. Both act tangentially in a direction opposite to that of motion. if they will be in the similar direction to that of motion, there will be a no resistance or no internal resistance. Okay, but if these are tangentially opposite to the direction of that motion, automatically there will be a opposing force, which means the motion will be opposed. Got it? Viscosity differs from the solid friction in respect that the viscous force acting between two layers of the liquid depends upon the area of the layers. The more the area, the more the viscosity will be. The relative velocity of two layers. Okay, like layer 1 and layer 2, they both having a different velocity. Okay, so what is the relative velocity? That will be considered. Distance between two layers. Less the distance, more the viscosity, more the distance, less the viscosity. The viscosity does not depend upon the normal reaction between two layers of the liquid. Like considering these three areas only, what is the area in contact between two layers? The more the area, more the viscosity. What is the relative velocity of two layers? More the velocity, less the viscosity, less the relative velocity, more the viscosity. Thereafter, distance between two layers, more the difference, high the viscosity, less the distance, sorry, more the distance, low the viscosity, less the distance, more the viscosity. And fourth, viscosity does not depend upon the normal reaction happening between the two layers of the liquid. It has nothing to do with the viscosity. Okay. The friction between two solid surfaces is independent of, now we are talking about the solid friction. Okay. The area of surface in contact. Like that thing which is particularly considered while considering the viscosity, that is not considered in the solid surfaces or in the solid friction. Why? Because the solid friction is not dependent on it, but it is independent on it. The relative velocity between them, again, this factor is considered while considering the viscosity. It is not considering while considering solid friction. Why? Because the solid friction is not dependent on it, but it is independent of it. The solid friction directly proportional to the normal reaction between surfaces in contact. Okay. Whereas the viscosity is normally not dependent on the reaction between the two layers. Now, Poiseuille's formula that we are required to understand as a point of discussion in this particular lecture. So we could say when a liquid flows through a horizontal tube with a steady flow under some external pressure. Okay, the liquid moves in cylindrical layers coaxial with the axis of the tube. Now here you can see in this picture. The velocity of the cylindrical layer is maximum along the axis of the tube and it goes on decreasing towards the wall of the tube. So we could say this is the axis. Here the velocity will be higher. But as we move close to the walls of the tube, the velocity will decreasing or will keep on decreasing. The velocity is minimum for the layer in contact with the wall of tube. And the layer which is in the immediate contact of this wall of tube, the velocity will be minimum. And the layer which is in the mid of this axis will have the high velocity because it's not having any kind of external force of friction. The velocity of different layers is shown by the arrowed lines in figure. Now, if you consider these arrow lines, so here you can say this arrow is the top modes. It's having the high velocity, then this having the decreasing velocity, this also, and this is having the minimum velocity. So now you can say as we move upward to the wall of the tube, the velocity of liquid is constantly decreasing. Okay, so that was the Poiseuille's observations. Poiseuille actually studied the rate of flow of a liquid through a horizontal capillary tube. Here you can say these are the capillary tube, and concluded that the volume V of the liquid flowing per second through a capillary tube varies directly as the pressure difference P across the two ends of the tube. Therefore, V is directly proportional to P. The more the pressure difference will be, the more the velocity. Directly as the fourth power of radius r of the tube, therefore V is directly proportional to R's power 4. Okay. Inversely as the length of the tube. Therefore, V is inversely proportional to 1 by L. The more the length, less the velocity. The shorter the length, more the velocity. Sorry, it's not the velocity, it's the volume V. Inversely as the coefficient of viscosity of the liquid, therefore V is inversely proportional to 1 by eta. Combining these factors we get V is directly proportional to P into R power 4 by eta into L, or V equals to pi PR4 by eta by eta into L, where pi by 8 is the constant of proportionality. This equation is actually called the Poiseiulle equation and is truly only for the steady flow of liquid through a horizontal capillary tube. After this, now let's have a look over the Stoke's law. So when a small spherical body moves through a viscous medium at rest, the layers of the medium touching the body are dragged along with it. But the layers of the medium away from the body are at rest. This causes a relative motion between the different layers of medium. As a result of this, a backward dragging force comes into play which opposes the motion of the body. This backward dragging force increases with the increase in velocity of the moving body. The more the velocity, the more the backward dragging force. Stoke found that the backward dragging force F acting on a small spherical body of radius r moving through a medium of coefficient of viscosity eta with velocity v is given by P equals to 6 pi eta PRO. This is called the Stoke's law of velocity. This is important for all of us. Kindly revise it and keep this in your mind. Importance of Stoke's law. This law is used in the determination of electronic charge with the help of Millikan's experiment. Please do not read it as a milkman's experiment. Oftenly we do it, but it is Millikan's experiment. This law accounts the formation of clouds, like how the clouds form. This law accounts why the speed of raindrops is less than that of a body falling freely with a constant velocity from the height of clouds. This law helps a man coming down with the help of a parachute. Now, terminal velocity. What do we mean by the terminal velocity? That is we required to understand. So let's have a discussion on this. So actually, terminal velocity, it is a maximum constant velocity acquired by a body while falling freely in a viscous medium. Okay, so when we can say any body that is falling freely in the viscous medium, so what is the maximum constant velocity it could acquire? That is known as the terminal velocity. Terminal velocity is represented by 2 pi r square into p minus sigma by into g by 9 eta, where p equals to density of falling body, sigma equals to density of the medium, r equals to radius of falling materials, g equals to acceleration due to the gravity. The following results follow from the above equation. The terminal velocity varies directly as the square of the radius of the body and inversely as the coefficient of viscosity of the medium. It is also depends upon densities of the body and the medium. What is the density of the body, what is the medium, that will also taken into the consideration. If P is smaller than sigma, the value of B negative, therefore the body will move up with a constant velocity. It is due to this reason that the gas bubbles rises up through soda water bottle. Like if you ever bought a soda and you just look at it, you will find out that gas bubbles rises up from the soda water. Why? Because of this. By knowing R, P and sigma and terminal velocity V, the coefficient of viscosity is calculated. So here we have finished this topic. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.